Hey guys, what we have today on the bench is a Peavey Windsor Studio, like a 15 watt combo amp. The client brought it in, he said he turned it on and played a little bit through it, but started smelling like smoke. So figured he'd bring it to me and see if I could figure out what's going on with it. It's a single-ended EL34 or 6L6 options. Looks like he had the chassis out. He didn't see anything wrong, but when he put the chassis back in, there's a couple little wires that didn't get tucked in properly. But it's basically two 12AX7s and an EL34 output. Yeah, kind of got a JCM 800, preamp, but after looking at the schematic, it's really not. It's got a solid state effects loop and solid state reverb on it, master control, standby on switch. In the back we have a regular power input socket, and then we have the speaker output with the ohms impedance selection. We also have a recording output, a remote switch for a boost channel, and then we have this power sponge, which I'm not really fond of. This is basically to attenuate the output power to where you can drive the power section hard, but it'll lower the volume down. These can be not very healthy for output tubes. So we're going to look at that. We're going to get the chassis out, see if we can see anything obvious with a visual inspection, and then do some measurements and see if we can't figure out what the problem is with the burning smell that he described. It does have a Celestion greenback in it, which is not stock to the amp. It's actually an upgrade. So we're gonna see that this is gonna be a printed circuit board with some possible issues. I talked with the client, and if it turns out that this isn't a real frugal to fix it, like if we repair whatever's wrong with it, if it looks like one of them situations where once we fix it, weeks down the road, another problem could arise just because of poor design and stuff. We may discuss with the client an option to, take out the printed circuit boards and just do a hand-wired kind of Marshall JCM 800 type circuit that he may be more happy with. So what we'll do now is I won't bore you with unscrewing the screws and stuff. We'll just take the chassis out, get it mounted on a stand, and we'll come back and take a look on the inside. Okay, so we got the chassis in the stand. I didn't see anything physically burnt. I brought it up to voltage. No, I didn't see any smoke, anything of that order. The client did mention that the standby switch was doing nothing, so like when it was in standby mode, it was still passing signal. I did check continuity where it gets to the board, which would be right here, and the standby actually is interrupting power to the screen on the power tube instead of a little bit earlier on where normally it would just be interrupting the plate voltage, allowing the tube to warm up, and then you kick it out of standby and the tube's ready to conduct current. So your voltage would go up to the typical voltage instead of going higher and then lower and down once the tube warms up. So that's kind of odd that they put it after the plate and before the screen. but it's doing nothing. So it's just always continuity happening there, whether it's in standby or not. So I don't know if that's a switch, the problem with a switch, or if it's, I've never really seen, those switches, when they fail, they usually fail open, they don't fail closed. Although, that could be the situation, or there's just continuity happening here all the time, and the switch has no effect on that if there's a continuity happening all the time. So yeah, I didn't notice anything right offhand. Excuse all the alligator clips and stuff. I was doing some testing. So in a nutshell, we got some figures here. We did some math, and what we have is a plate voltage of 459 volts with 32 volts present at the cathode. It's cathode biased amp. Across, and then so subtract the 32 from 459, and you have a plate to cathode voltage of 427 across actual 400 ohm cathode resistor. So in a cathode biased amp, 49 milliamps would be cool, average would be 55.6, and max 100% would be 58.5. So doing the math on these numbers here, we come up with 75.6 milliamps of plate current at 32.3 watts dissipation, which is 129.2% of max safe dissipation. So when we would like to see maybe 55 milliamps, we got 75, which is well over the max of 58. And this is the way it come from the factory. The schematic has that 400 ohm cathode resistor. So I just did a vibro champ that had a similar issue at about 120% with the 470 ohm resistor. Again, different tubes and all that, but still doing the math, we're running way hot on this tube with the factory 400 ohm cathode resistor. So the plan will be to go up to more than likely a 1K 1000 ohm resistor, which will up our plate voltage just a tad and up our cathode voltage some, but it will bring down this 75, and our ideal goal will be somewhere around 55, 56 milliamps for average plate dissipation. So that's where we're at there. What we're going to do next is, in the cathode resistor would be this guy. If I can get my pencil in there. This guy right here is our cathode resistor, and that's the 400 ohm resistor. So what we want to do is we want to change that to at least 1K. We might even go to 1.2K to get that bias within reasonable limits. Again, I didn't see it smoke. I didn't see any smoke anywhere. I didn't smell anything. I only had it on for maybe 15 minutes. And the part components, I didn't see any discoloration or any of that. However, definitely, and I didn't see the tube red plating, but running it at 120, over 120% of its max dissipation just isn't, I just don't get it. I don't know why they got to run them so hot. But a lot of amps are like that. You buy them, and they come out biased incredibly hot. So we're gonna, to prevent it eating up tubes or other possible failures, because of drawing so much current. Again, this is PCB mounted power tube, PCB mounted preamp tubes, or PCB mounted. Those don't really concern me as much as a power tube that's pulling that much current mounted to a PCB board, and the resistor will get hot, and it's mounted right directly to the board. So if this resistor gets too hot, more than likely it's going to burn through that circuit board and burn up traces. That could, potentially lead to a even worse failure that could cause issues with the power transformer or output transformer for that matter. But yeah, the first thing we want to address is that cathode resistor. See if we can get our numbers correct, get them at least within tolerances of the tube. And and once we do that, if everything's okay, we're going to kind of look into that the power soak function. I'm really not a big fan of the attenuation on these that could be another failure point. And also the where the standby switch goes into the circuit board. We'll have to get the circuit board out and remove the standby switch leads and just see if the standby switch is bad, we can replace it. I also have a notion to just go ahead and bridge that, and then for a standby switch we can tap in before the rectifier and just interrupt the AC from the rectifier and then do our standby here, or we could do it post rectifier and use our standby to interrupt the plate voltage on most amplifiers. So that'll be something I'll discuss with the client, and either way we may just wind up finding out that the switch is bad, or there's something conducting on the board that we can deal with and fix and leave the standby where it is. I'm really, again though, not a fan of having the standby at the screen instead of having the standby at the plate. Because if you have the standby before the filter caps, then when you turn on the amp and you're supplying heater voltage to the tubes get warmed up, and then when you kick it out of standby, then you're delivering the high voltage to the filter caps. And if the tube is already warm, then the voltage will just climb to, say, 460 volts and stay there. If the tubes aren't warmed up, which if you bypass and you're at the screens, then the capacitors are the inrush is gonna be higher than that. These are 550 volt capacitors, and I'll bet anything that the inrush cruises right up to about 550, and then as the tube warms up, it'll lower back down to about 460. So it's just this way. If you have the standby before the filter caps, it allows the tubes to warm up, and then when you turn the standby on, the tuber is already going to be ready to draw current, and you won't have, the inrush will just go up to normal operating voltage without going up higher and then coming down lower. So these things I'll discuss with the client. But once we get that done, like I said, the cathode resistor, change the value of that, get the bias under control. Then I'll obviously address the standby switch. After I get back with speaking with the client, we'll come back and we'll show you what we did as far as the cathode resistor issue, the standby switch issue, and we'll give you some updated numbers and on the bias and on a final assessment, and then we'll play through it and see how it sounds and all that. And we'll just come back to that. Okay, so on the underside of the board where the power tube is, we have the plate voltage coming in here, and on the other side of the board it goes to pin 3, which is the plate, And then the standby switch comes along this other rail that goes to pin 4, which is the screen. Well, we have some black carbon buildup, got hot. So basically what we have is we have a short between the plate and the screen here. So that's why the standby switch wasn't working. I disconnected the standby switch and it works fine. But when your plate and your screen are connected together, the standby is not going to work. That's also going to affect the bias of, you know, the current draw on the tube. So in this, unfortunately, I think this carbon goes completely through to the other trace on the opposite side of the board that basically crosses over this trace to go to the plate, whereas this trace goes to the next pin on this side of the board to the screen. If I flip over the board, if I can do this and be able to show it. So right here is where the plate goes to, the plate voltage goes to the plate, and then on the underside the screen voltage goes to the screen, and it crosses over this, but I believe that all the carbon, it's just made it completely conductive, and it's just going to be a short. The only way I think I may be able to work around this is to eliminate this trace and just solder the plate wire directly to the plate, and then on the other side, if I can get this thing to cooperate here, on the other side where this trace goes to the screen, looks okay as long as we don't have voltage present here shorting out with this by means of going across it and being all conductive. So in other words, the plate voltage, I may remove the plate voltage from this terminal, spade terminal here, and just run the plate voltage wire directly to the plate so it's not also connected to the screen. And then the standby switch should work fine, and that'll just take a little bit of work. Get rid of this spade and then the connector, and remove the voltage from this point completely and just mount it directly to the tube. This is why I do not like printed circuit boards with power tubes connected, because they just always have these kind of problems where you got a lot of current going on, carbon builds up, they buy us some hot from the factory, and the carbon buildup happens, and then that makes a connection, which the plate voltage will be at 1 voltage, and then you want your screen voltage a little lower than that. And in this case, it was just feeding the plate and the screen the same voltage. Just a bad situation. So I'll discuss it with the client, and we may try to just eliminate the plate voltage from here so it's not shorting to the screen, and just connect the plate voltage directly to the plate on the tube socket itself. Because I don't believe I'm going to be able to make this. I think it goes through the board and it makes contact on both sides. So it'd be a matter of basically completely cutting this out and then rerouting the plate voltage, or the plate line would have to be, because like I said, it goes through, so I just have to run this wire, which supplies the plate voltage, straight to the plate right here on a tube terminal, and just and then there won't be any voltage present here, and get rid of this trace and just run it there, and then that way I can have my screen voltage unaffected by this plate. But it kind of burned through, and just not a good situation. So that would need to be fixed first, and then readjust you know, and reconsider the 400 ohm cathode resistor, because that's going to affect the bias when they're both seeing the same voltage, and it's not good for the caps, it's not good for anything. So that's going to be the project we work on. And I'll discuss it with the client when we come up with a workaround. We may do that, and also he may consider just pitching this board, and we could go with chassis mounted tube sockets and do a point-to-point like JCM 800 type build inside of this chassis if we decide to just ditch the board. But we might be able to, like I said, we might be able to just run the plate voltage directly here, separate the short so we can have individual plate and screen voltages. And we'll check back with you once we find out something. Okay, so this yellow wire here is where I removed the trace that kind of comes from along here and runs to here. I terminated the trace here and ran a wire from here to the screen on the tube socket. This like light gray area where it makes the corner here is the trace has been removed, and right here where the high voltage is from the transformer that goes to the plate, that's where it was shortened on the other side of the board, or through the board rather, with the carbon and everything, shortened to this trace, given the same voltage to the screen as it was given to the plate, which will definitely affect the bias. But yeah, the simple down and dirty fix was to just peel this trace off from the pin to about right here, and then just replace that trace with an insulated wire to where it's not going to be coming in contact with the high voltage from the output transformer to the plate. So, and that rectified the standby switch, because with the plate, you know, the standby is located right before the screen. So when the screen is shorted to the plate, it's going to always be on, and the standby switch will have no effect on it. But now that they're not shorted, the standby switch will open the circuit to the screen, allowing no voltage to get to the screen unless the standby is switched on. So we're going to put it back together and go ahead and recheck our measurements and see if our bias has lowered, and then see how high it is, and then see if we need to correct that with the cathode resistor. Here is that spade connector. If I can get my pencil in there, that spade connector. Then there's the trace on top of the board to the plate. Well, on the underneath side, the other trace came across and went over here to the screen, and right in there is where the burn spot is on the back side, where it was making contact with this trace and the plate. So I don't think this trace looks in good condition. I don't think I'm gonna have to do anything with that. I did clean up any carbon residue and stuff from that. Cleaned up, there was carbon residue on a couple other spots too, I cleaned up. But that trace looks okay. And then you flip over, and again you can see where that trace on the other side goes straight to the plate, but it overlapped the if I can get a hand on the camera right, it overlapped the this elbow here, and that's where the short was occurring. So we just kind of bypassed around it, got rid of that the bottom side trace for the screen, and bypassed around it with this yellow wire here that's insulated, and that rectifies the problem. So Like I said, I'll refire it up, do some more measurements, see where we're at, and go from there. Okay, we're back, and I fixed, in the previous shot I showed you, I fixed the, where is it? I fixed the underside of the board here with the wire to the screen. So now we have, about 30 less volts on the screen than we do on the plate, which is what we're supposed to have. And when I did that, our numbers, we went from 75 milliamps at 32 watts at 129% dissipation by just fixing that screen voltage issue, which also corrected the standby switch issue. We brought it down to 66.1 milliamps at 29 watts at 116%, which is definitely cooler than the 129%. We did definitely cool it down a bit. It's still kind of hot, So we replaced the cathode resistor, this guy right here, this resistor right here, we replaced from a 400 ohm to an 820 ohm. Well, actually about 814 actual ohms, which bumped our plate voltage up a little bit and the cathode voltage up a bit. But we brought it down to 39.5 milliamps at 17.9 watts at 71.6%. It's a little bit on the cool side, but it's actually, I'm pretty comfortable with that. Especially if this type of amp, they'll change out tubes from EL34 to 6L6 or 6550, and I'd rather be on the cool side just in case when they change a tube out, they're pretty well guaranteed that the bias is not going to be super hot. So it's just a little bit below cool, for a cathode bias, but it sounds good, and we're gonna be happy with that. So that should wrap this up. It for a PCB board type tube amp with the power tube mounted to the PC board itself, you'll have these kind of problems. They ran one trace on the bottom of the board over the top of this trace, or on the other side, but crisscrossed it, and then the current draw created heat, and carbon developed and burnt through the two traces, and basically shorted this trace to the one on the other side feeding the screen. So now with that wire in there, we've separated the screen and the plate, and it allows for our bias switch right here. When we turn the bias switch off, we're no longer getting screen voltage. When you turn it on, it applies voltage to the screen the way it's supposed to. But the screen voltage has to be lower than the plate voltage. That reduced the bias significantly. Once we fixed that issue, again, we dropped the bias from 129% down to 116%, which you want to be below 100. And then when we upped the cathode resistor value from 400 to 800, we dropped it down to 71%, which is what I'm happy with. So that should wrap that part up, and then we'll put it all back together and do a little demo of it. Okay, now for a little demo.